This is Georgios Patounas presenting the paper on the utility of coarse-grained mobile network telemetry in detecting performance degradation. With this work, we investigate whether passive coarse-grained measurements from the edge of the mobile network can effectively be used to automatically infer the end user's quality of experience. With the next generation mobile networks coming online, the requirements for service assurance become stricter for a number of use cases, like critical services, that require high reliability and low latency, meaning almost real-time performance monitoring. Nevertheless, the vast majority of everyday users will still be looking for generic mobile broadband access, such as what is provided by networks today. At the same time, operators are looking for solutions to improving service assurance with minimal cost and overhead, in support of the increased user population, traffic, and performance expectations. This is exactly the area that we target with this research, with the goal of providing accurate service assurance with a low barrier of entry and low overhead for non-critical use cases. Looking at the generic topology of an LTE network, the first point of contact for the network's users are the base stations, called the eNode Bs. From there, traffic is forwarded through the core network towards the internet. The base stations keep track of a range of metrics referred to as the Cell Key Performance Indicators, or KPIs. These are coarse-grained aggregates, often reported every hour, and are typically used to characterize a base station's performance over a long time scale, in absence of direct correlation with the user's quality of experience, basically relegating the KPIs to the province of long-term network planning. What we want to investigate is whether we can get more value out of them. By fusing them with active measurements from the point of view of the users, we aim to provide a mean for quickly and automatically flagging poor performance for services like generic mobile broadband. To take a look at how we do that, we leverage the Nornet Edge infrastructure, which is a Norwegian testbed dedicated to measurements and experimentations on operational mobile networks. It consists of geographically distributed measurement nodes and server-side infrastructure for the collection of measurements. A measurement node looks like this, with a single board computer running a standard Linux distribution and connected to mobile networks through off-the-shelf modems. The KPI logs from the base stations that serve the nodes are provided by Telenor, a nationwide network operator in Norway. Putting this in the context of the LTE network, the measurement nodes take the place of user equipment to perform measurements against an eco server. Each measurement node sends a packet to the server every second. The packets sent and received and their mean round-trip time are then aggregated into 5-minute bins. In addition, metadata is collected every minute that includes the ID of the base station that is currently serving the node. In summary, the data sets look like this. We have the KPIs of each base station aggregated over periods of 60 minutes, the active measurements of node performance aggregated over periods of 5 minutes, and the metadata for the nodes collected every minute. To create a unified dataset, we filter out inconsistencies and periods when the nodes rapidly switched between base stations. Because of the 5-minute aggregation of active measurements provided by the testbed, we would not have sufficient information to determine which base station is responsible for the end-user performance observed. Finally, using the metadata, we can match the active measurements of user performance to the relevant base station's KPIs. As a sample, this is a snapshot of a day of measurements with 2 cell KPIs that characterize user traffic patterns on the top figure and the performance of a specific node on the bottom. The main objective of our work then is to classify each of the given hours as problematic or not, based on the KPIs coming from the base stations. Since we're interested in the actual quality of experience of the users, we use the active measurements performed by the nodes to define what constitutes a period of degraded performance. We define 3 thresholds: the packet loss rate, the round-trip time, and the frequency of violations of the above. The packet loss rate threshold is defined globally and measured in packet loss per second over 5-minute periods, while the round-trip time is defined for each node separately as a percentage of its lifetime round-trip times. This is to account for persistent characteristics of the nodes, which give them distinct round-trip time patterns. The violation frequency is defined as the number of 5-minute bins that exceed one of the above thresholds within an hour of measurements. We evaluated a wide range of these thresholds individually to understand how they affect the accuracy of classification. Here we saw a sample of their performance in terms of accuracy, precision, and recall for packet loss, round-trip time, and frequency of threshold violation. On average, all combinations achieve high accuracy, and more importantly, the high recall values that indicate 90% of anomalies can be consistently identified. Adopting then the perspective of a network operator, we settle on two final thresholds, combining the above parameters. The low level is meant to flag performance degradation that does not necessarily warrant immediate attention, but may be interesting to examine, while the high level is reserved for severe performance degradation that should be immediately tended to. As our task is binary classification, machine learning offers a number of approaches that can gracefully handle the large number of features, in this case our KPIs, and provide automated classification through supervised learning, in this case the labels given by the user's quality of experience. We tested multiple classification algorithms using the combination of all mentioned thresholds. Random search was used to search the configuration space for the algorithms, and k-fold validation ensured the validity of our results. In addition, the ADASYN algorithm was used to balance the datasets by generating synthetic data. Based on the evaluation showed here, we selected the random forest classifier, which provided the most accurate and consistent results. Moving on to the main part of our evaluation, something that needs to be taken into account when training the classifiers is the case of hours containing handovers. These are periods when a node has been served by multiple base stations. Handovers by nature introduce delay and an elevated risk of packet loss. Therefore, we examine the performance of hours that include handovers separately from the ones that don't. Splitting the dataset in this way provides two benefits. Firstly, the dataset containing the hours of single-cell operation will remain unaffected by the handovers, which are already a well-established cause of performance degradation. Secondly, the dataset containing just the hours of handovers will establish a new baseline for user performance and the correlated KPIs. This will allow the classifier to be trained in detecting causes of performance degradation other than the handovers. To compare the performance of the classifiers for each of the thresholds, we examined the corresponding receiver operating characteristic curves and the F-score. A ROC curve is commonly used to visualize the performance of classifiers over varying thresholds, while the F-score considers the precision and recall in a unified metric. Examining here the dataset containing no handovers, we find that both levels of thresholds perform well, achieving an area under the curve approaching 1, and an F-score of 0.9 for the low threshold and 0.94 for the high threshold. Looking closer at the worst case here of the low threshold and translating it to the exact numbers of correct and incorrect predictions, out of 321 anomalous hours in our test dataset, just 9% was not identified, being a false negative. The false positives are also fairly low, with 14% of normal hours incorrectly suspected to be anomalous. That means that of the performance degradations experienced by an end user, even the benign ones, 91% of them were identifiable by the aggregate cell KPIs. The remaining false positives can be explained by degradations that are reflected in the KPIs but only impact a fraction of the connected users, which may not involve our measurement node. The false negatives, on the other hand, can be caused by degradations that are not reflected in the KPIs at all, such as packet loss that could be occurring in the core network. Having confirmed that we can successfully identify a user performance degradation, we turn to feature selection to understand the root cause of the incidents. Here, we have a number of categories for the KPIs that we examine, and it is evident that in this case where no handovers have occurred, the integrity and stability of the cell is directly linked to the user's experience. The top KPIs here characterize the number of users connected to a cell. Taking a closer look at them and coloring their values according to the normal and anomalous hours, we see a longer tail during the anomalies, that is, a higher mean and more variability, meaning that the anomalies tend to happen in periods of elevated or abnormal user activity. Moving on to the cases of handovers, some additional consideration is required. In each hour, a node will be connected to multiple cells, meaning that multiple sets of KPIs will be relevant to its performance. A methodology is then needed to select the set of features that will be associated with the observed user performance. Once we take into account that in our work we are only dealing with stationary nodes, meaning that the handovers examined are not initiated by physical movement of the user out of the cell's area, we can make some assumptions about the reason that led to the handover. The standards dictate that the handover decision depends mainly on the signal strength provided to the user equipment. Once this signal strength is lower and a predetermined threshold has been reached, a better alternative is sought and a handover is initiated. Such conditions are frequently met when the mobile user equipment is moving out of the coverage area of a cell. However, a stationary user will tend to connect to a single cell that consistently provides the best performance due to physical proximity. Examining our nodes, we notice that their majority does indeed favor a single dominant cell. A handover away from the dominant cell, then, can be an indication of performance degradation or complete cell unavailability. Considering the above, we explore two approaches to labeling the cells. Firstly, we naively blame all cells to which a node has connected to during an anomalous hour. Secondly, we intelligently blame the previously identified dominant cell for each node. Next, we will compare the performance for both thresholds and approaches. Following the first approach, the high threshold performs very similarly to our previous results. However, the low threshold performance is significantly worse. This can be attributed to the nature of this dataset, which is made up of hours that are expected to, on average, experience worse performance due to the presence of handovers, which could be masking mild performance degradations. Next, we examine the most important KPIs as before. Here it is immediately evident that a higher than normal incidence of handover-related events is a clear marker for performance degradation, with the top three features this time belonging to the category of mobility KPIs. Moving on to the approach considering the stationary state of our nodes, when the dominant cell is blamed, both thresholds achieve very high levels of performance, with areas under the curve approaching 1 and f-scores exceeding 0.9. As a reference, approximately just 1% of the anomalous periods were not identified in this case. When focusing on the dominant cell only, the KPI importance uncovers the underlying root cause of the anomaly. Mobility KPIs play now a minor role, with integrity and stability once again becoming the top contributors to the classification. This shows that handovers are initiated due to the overwhelming traffic or the cell becoming unavailable. The combination of the root cause and the solution of handing over strongly affects user-end performance. For the final part of our evaluation, we briefly examine whether feature selection can also be used to minimize the overhead of KPI collection and processing, while maintaining comparable success of identifying performance degradations. As seen here, the results are very promising. By using just 10 most important features, we can achieve performance closely matching the one produced by the full set of 76. These results cover the case of no handovers, but the same success was observed for the case of handovers. In conclusion, we find that almost all episodes of degraded performance correlate well with changes in cell KPIs. This agrees with the common wisdom that the majority of performance issues faced by the users are related to the radio access network. It could also indicate that problems outside the radio access network are still imprinted in the cell KPIs. We presented a methodology for automating detection of network problems that would demonstrably affect the user's quality of experience. The results are extremely promising, with over 90% accuracy in inferring problematic hours. Further, it was possible to identify primary and auxiliary causes to the performance loss by intelligently splitting the dataset and analyzing KPI importance. We used coarse-grained measurements that are already being produced by operational networks and a simple machine learning approach. This makes for a very low overhead of data collection and processing and minimal barriers to entry for a network operator, hopefully paving the way for better service assurance in non-critical services. Thank you.